Okay, so it is my great pleasure to welcome Daisuke Nagai here, who is a Steve Murray Distinguished Lecturer, and he is visiting us from here. Actually, he is now in Europe, in Germany, on sabbatical, but he came back because he wanted to come so bad here this particular week. So Daisuke is visiting us this week, here this morning, and he will be here until Friday afternoon. And he's currently sitting in Bill Foreman's office, which is B408. And I circulated his schedule earlier this week, so if you want to sign up to meet him, he still has available slots. So you can either try to find him in B408 or just put your name on his schedule. So Daisuke obtained his PhD from the University of Chicago. After that, he became a postdoc at Caltech. Then he immediately moved to Yale, where he became an assistant professor. And shortly after, a couple years after, he was appointed as an associate professor there. Daisuke is currently the co-director of the Yale Center for Research Computing as well, so he's very busy with simulations. So Daisuke's main research interest is to understand the origin, composition, and structure formation of the universe. And Daisuke's current research focuses on theoretical and computational cosmology that are closely connected to experiments and observations. And in today's presentation, we are going to hear about multiband HD cluster cosmology, new frontiers of cosmology and astrophysics. So, thank you.
Thank you very much. Thank you for a kind invitation. And it's such an honor to actually be part of this distinguished the Scholar program. I have known Stephen for many years, and it's just such a body of work that he has done for the X-ray community. And I would like to discuss some of the new development that is happening in these general directions of using X-ray astronomy combined with the high-energy astrophysical processes to learn about the universe and the physics of the universe. So the title of my talk is this multi-band high-definition cluster cosmology. In the 21st century, the universe became the laboratory for understanding the physics of the cosmos, and the amount of data that are coming online is just enormous. And there's bright future in these areas of trying to gain additional information about the formation and evolution of the universe, and trying to actually use the universe as a laboratory for understanding the fundamental physics. So I would like to discuss the sort of interconnect and some of the research that can be done at the crossroad of cosmology and astrophysics. So I will go back and forth between trying to understand deeply about the physical processes, astrophysical processes happening in the formation of galaxy clusters, but sometimes pulling back and to see if we can apply those knowledge to actually learn about the physics of the universe and cosmology. So this is the list of, in today's presentation, I'll be presenting some of the work that we have been doing in collaboration with many of the people here in US and also around the world. So the idea of using galaxy cluster, which is the largest the gravitational bound object in the universe, and use that fairly complex systems to learn about cosmology is not an old idea. It's been around since 1930 when Fritz Zwicky was actually measuring motions of galaxies in clusters, and which led to this realization that the universe has a lot of dark stuff in it. So that was the start of this discovery of dark matter that we have been after, and we have yet to actually find a clear solution, a physical understanding as to what that is made of. In 2005, we've seen this beautiful picture taken by the Hubble Space Telescope combined with the Chandra Space Telescope, which with a single snapshot, it proved to us that something like dark matter seems to exist. We cannot rely on the distribution of baryons and modify gravity on large scale in order to describe these pictures. So that was sort of a nail in the coffin that, yes, the dark matter seems to exist. In fact, this is just one galaxy clusters, but you can actually even think about using the individual galaxies that are falling into the galaxy cluster. Each of them act kind of like a bullet too. So there is a frontier in trying to understand the nature of dark matter by actually studying the distributions of baryon, compare that to the mass distribution mapped out by gravitational lensing. So here's one example where the researchers are actually trying to seek any offsets between stars, gas, and distribution of dark matter mapped out by the high-resolution gravitational lensing images. And these results, sometimes you see some offset, but then when you do the follow-up observation, these offsets don't really exist. But as you do these measurements, you're actually pushing the limit of this so-called self-interacting cross-section of the dark matter. And there's some of the tighter limits actually comes from using galaxy clusters and also galaxy embedded in clusters to learn about this fundamental physics. In 2010, people have been very creative, and one can actually use galaxy clusters and in its evolution to learn about dark energy as well. The idea is as follows. The galaxy cluster grow by accreting material through the gravitational pull. But the gravitational pull that are given by the dark matter is counteracted by the repulsive force of dark energy. So it's really the balance of these two forces that are basically ultimately determine the rate at which the galaxy cluster accrete mass and how they grow in the universe. So in principle, if we stare at one of these galaxies or dark matter clumps, and if you see them move, you can use this as a force balance test. In principle, we actually do large cosmological survey and count number of galaxy cluster as a function of redshift. And that gives us information about that's a sort of that's a statistical way of actually doing this kind of force balance test, but do this in a statistical way. So there has been the number of very interesting constraints. You can detect the effect of dark energy on the growth of galaxy clusters, and some of the state-of-the-art measurement has been made using things like Chandra Space Telescope to estimate the masses of the galaxy clusters and count them as a function of redshift. The future of this field is actually rather is very bright. In coming year, the next generation X-ray telescope is scheduled to launch in 2019. It's called eROSITA. It's a German-Russian mission, scheduled to survey the whole sky for 4 years and expect to detect 150,000 galaxy groups and clusters out to redshift of 1.5. Just to put this in a reference, we currently have something of order 1,000 galaxies, several thousand galaxy clusters from Planck survey, as well as the X-ray surveys. This new mission that is currently designed and scheduled to launch sometime very soon will increase the statistical sample of galaxy cluster by several orders of magnitude. So that's in the X-ray side. There's also equally just as exciting development happening in microwave and optical side. Here's a couple of examples from the South Pole South Pole Telescope and also Atacama Cosmology telescopes in Chile. And they are actually observing the galaxy clusters in microwave. Okay. Just to give you a sense of how this so-called low noise, high resolution frontier has done to us. This is just this example from microwave, where back in 1990 started with the COBE satellite, which had this angular resolution of order 110 degrees, which found the isotropy, some of the best black body radiation, but at the same time has also discovered the anisotropy in the cosmic microwave background, which led to the discovery of the initial quantum fluctuations in the early universe. However, over the last every decade or so, with WMAP and Planck, the angular resolution and both angular resolution and sensitivity have been improving significantly, often by order of magnitude. And we have seen many of the exciting results about the physics of the universe from this so-called low noise, high energy, high resolution frontier. At the moment, with the SPT and ACT, the angular resolution of this survey is of order 1 arc minute, which is typically the size of the galaxy cluster extended in the sky. So one of the new effects that comes online, in addition to studying the cosmic microwave background in the early universe, is to use cosmic microwave background as a backlight to actually study the structural formation in the universe. One important effect that is embedded within this in this CMB signal is called Sunyaev-Zeldovich Effect, named after the two Russian scientists who discovered that effect. The idea is that you start with the perfect blackbody spectrum of the cosmic microwave background. These low-energy photons traverse through the universe and interacts with the hot electrons embedded within the galaxy clusters. And then the photon actually experiences this so-called inverse Compton scattering because the energy of the photon is very low, the energy of the electron is very high. So experience this thing called, through this inverse Compton scattering, the photons that scatters with the electrons are kicked up in energy. So this is a bit of exaggeration in terms of magnitude, but it makes a point. This Sunyaev-Zeldovich effect has this very unique spectral feature. At 217 gigahertz, there's no change. Number of photons are conserved, so you see this crossover frequency. Below 217 gigahertz, you see hole in the CMB sky in the direction of galaxy clusters. Above 217 gigahertz, if you look in the direction of galaxy clusters, you see additional enhancement of the CMB signal in the direction of galaxy clusters. This creates this unmistakable signal that can be used to actually detect galaxy clusters. The nice thing about the SZ effect is that it's redshift independent. The reason is that this is a sort of absorption mechanism. So as long as the electron exists and the galaxy cluster exists, it doesn't matter where the galaxy clusters are located. This is an illustration that you take this galaxy cluster from redshift of 0.2 out to redshift of 0.8 or so. With roughly the same amount of time, you can detect galaxy clusters of the similar masses. In contrast to the emissive source. If you have a light bulb, you put it farther away, the flux that you receive gets dimmer and dimmer. So you need to integrate more time in order to get the same signal. That's not the case for the SZ effect. So that has a unique signature. In addition to that, the SZ effect is also approximately proportional to mass. So when you select the galaxy cluster, you can not only find them out to high redshift, but you can also select them in a way that is more or less mass dependent. So that creates the very beautiful sample, which has allowed us to actually use this as a cosmological probe. A number of cosmology papers has been written based on the sample that has been collected from SPT, ACT, and Planck. Now, of course, the high-resolution frontier is the future for the CMB. X-ray community has been doing this in the ultra-high resolution. So these are the two examples that I just selected from the beautiful images of the central regions of the Perseus cluster, which shows the energy injection from the supermassive, presumably the supermassive black hole sitting in the center of the galaxy cluster, interacting with the surrounding medium, heating up the gas. Another exciting observation comes from one from Alexei Viklinin here at SAO, which has spent 2.4 megasecond exposure, did the mapping of the outskirts of the galaxy clusters, and you can detect the X-ray photons out to very large radii. Pretty much most of the virialized regions of the galaxy clusters has been detected. And then the third tool is the gravitational lensing. This is another growing field from HST to Sloan Digital Sky Survey, Dark Energy Survey, and LSST in the future. These missions will provide very detailed maps of the mass of the galaxy clusters through these gravitational lensing arc, not just a strong lensing, but also weak lensing. So we have many tools that we can use to study the evolution, define galaxy clusters, study their mass and its evolution. And here's the state of the art of what we can do once you collect all these samples, do the analysis. You can learn about the competitive constraints on things like the equation of state of dark energy, matter density of the universe, but there is also a problem. The problem is noted by the Planck collaboration. It's known as the CMB cluster tension, that the cosmological parameter derived from the CMB, which is a traditional way of actually studying cosmology, seems to be in tension with the galaxy clusters. So that's something but these tensions are very important. There are multiple ways of measuring same quantities, and galaxy clusters are starting to become a probe of cosmology, but the tool is very different from the cosmic microwave background, which is at small density fluctuations based on a linear theory. On the other hand, galaxy clusters are complex gravitational bound object, gravitational collapsed object. which depends on this more complex astrophysical processes. Nevertheless, one can actually, there is an information in here, and one of the important frontier, and one of the major problem here is this thing called mass calibration, and it's also about the selection function, how the galaxy clusters are selected. Those are two main issues facing this, are the use of galaxy cluster as a cosmological probe. But probably the most important one, this thing called the mass calibration, there's a lot of work going on, and as you probably notice in AstroPH, every week, maybe sometimes every other days, that you see new lensing measurements and constraints that are improving these tensions, almost at the verge of resolving much of these tension from both gravitational lensing of galaxy as well as the gravitational lensing of cosmic microwave background, which is a very rapidly developing field. Looking into the future, here is some of the forecasts of what Eurosita and this so-called CMB+4, the stage 4 experiment, under consideration for the next generation CMB mission, might be able to do. And this just gives us a sense of the kinds of cosmological information that are actually embedded within these Eurosita data or the future CMB+4 data. So things like sigma A, W naught, the change in equation of state WA, as well as neutrino mass, are some of the interesting cosmological information that one can get at in principle in terms of statistics. Okay. So that's sort of a more well-established technique that we know in this community that we can hone in on. But I like to talk about this sort of new path in this field. And the new path here that I'm going to talking a little bit more about extensively in this talk today, because we want to be forward-looking and looking for new signal, is this thing called kinematic SZ effect. This effect happens because of the motion of the galaxy clusters. When galaxy clusters are actually moving with respect to cosmic microwave background, the electrons actually that's embedded in galaxy clusters see anisotropic distributions of photons from CMB because of the motions of the galaxy clusters. So when you go back to the electron's frame, then the radiation, the scattering process is also anisotropic. So that creates this thing called kinematic SZ effect due to the peculiar velocity, the motions of galaxy clusters in space. So that's interesting information because we can actually measure motions of the dark matter halo as opposed to thermal energy content of the dark matter halo, which is what we have been mainly doing with things like Planck data or the SPT or ACT data. Most of the signal that we have detected and have used for the cosmological application or astrophysical application had been mostly on this much bigger signal that are easier to detect. But there is this interesting signal which tells us about the velocity structure as opposed to density distribution in the universe. So that's something quite exciting. The problem, of course, is that the signal is actually quite small. It also has this spectral shape, basically identical to cosmic microwave background, so you don't have this unique spectral signature that we could use to unmistakably measure the kinematic SZ effect. So that has been challenging. This effect has been measured for a number of merging clusters in a nearby universe, but has been limited to few objects as opposed to doing this for many hundreds and thousands of objects. However, the cosmologist has been somewhat inventive. There is actually a way to pull out this signal from the large cosmological map, and that technique is actually called the Pairwise KSZ effect. The idea is the following. You have this, so there are many galaxy clusters in space, and they are separated by some distance r and some redshift z in 3 dimension, if you will. And that because the gravity is attractive, that these motions of galaxies, velocity of object 1 and object 2 are always attracting each other. It's just the nature of gravity. So this so-called the pairwise velocity, the velocity the product of those velocity of 2 objects is always a negative number. Okay? The kinematic SZ effect effectively measure, so you can construct a statistic using kinematic SZ effect, basically multiplying the kinematic SZ signal of this object with kinematic SZ signal of the other object, and you can construct a statistics that is dependent, that can measure this pairwise velocity, but you're always weighted by the amount of electrons that are actually doing the scattering, which controls the amplitude of the kinematic SZ effect. So that this is the statistics that one can actually measure from the CMB map, and that the pairwise velocity contains the interesting information about cosmology. However, there's also the optical depth, which is the total number of electrons in halo, is something that depends on astrophysics. So this signal, we have both informations about cosmology and astrophysics. If we can learn how to actually measure the optical depth, in principle, we can use this velocity as a cosmological probe as well. Just for the information, maybe a little technical, that this pairwise velocity depends on the things like growth function and sigma A in a way that's different from the thermal SZ effect. Okay, but I will remind you that the signal that we detect using this technique depends on both cosmology and astrophysics. Okay. The reason why this is exciting is that this signal was actually detected in 2012, fairly recently. This is from the Act and Boss collaboration. A number of experiments have actually produced this images, and again, here is the effect is negative because of the attractive force between the two halos. And but the interesting thing, exciting thing is that the measurements are actually improving very rapidly. So a number of paper has been written because this is such a rather growing field and also the nascent field. That there's a number of forecast paper came out in the last couple of years predicting what that expected signal noise will look like with future experiment, like South Pole Telescope, SPT3G, DES, DESI, and so forth. And one of the authors actually asked, will kinematic SZ effect measurement enhance the science return from galaxy survey? Well, basically what we're doing is we're actually finding the locations of where the dark matter halo is using galaxy survey, and then stacking the CMB, they're looking for the CMB pixels associated with that region, and then computing the statistics. So you're really combining the galaxy survey with the CMB surveys. And the author have concluded, yes. Good. All right. More specifically, this is a figure from that same author, Sugiyama et al. 2016. This is the kinds of improvement that you can get in red compared to one without kinematic SZ effect. And yes, you do get improvements on things like angular diameter distance or Hubble parameter and so forth. But another important plot here is that you always have to marginalize over the optical depth of the galaxy clusters, as we just discussed, since kinematic SZ effect is sensitive to the amount of electron that we see along line of sight. If you look more closely to this optical depth, you can, in principle, you can use the data to actually solve for the optical depth to about 20% or so. But if there is an external prior on the optical depth better than 20%, then we're really just going after all of these cosmological signals. So that's one benchmark, is that the problem number two, in addition to the cluster mass calibration that I have talked about, is that we are looking for external prior. If we were to use this technique for cosmology, we would need the prior on the optical depth at the level about 20%. Then we're in the good footing. Okay? Just to give you a sense of how important that sort of velocity measurement will be, this is another kind of plot that you can actually, the velocity structure is very sensitive to things like different types of modified gravity. You can distinguish these models in principle if you can actually turn this kinematic SZ effect as a tool for cosmology. But the problem is the optical depth. Okay? So there are several ways that we can actually model this optical depth or the signal that we're seeing in the CMB map. One way is to actually use hydro simulations to directly, this is a sort of full physics, multiscale, multiphysics simulations of the evolution of dark matter, gas, and stars. And this is a very growing field. Computer simulation got fast enough, the algorithm and subgrid model has become sophisticated enough, calibrated to wealth of observations in galaxy surveys, has given us some confidence that we can actually realistically simulate the gaseous medium in galaxies and galaxy clusters. Okay. So that's one way. Of course, it is difficult to actually do this kind of simulations for the large cosmological survey that we have been talking about. So at the moment, we have this extreme dynamic range problem that the simulations are still prohibitively extensive. The second way that people have been exploring in this cosmological survey is to take the slightly much cheaper n-body simulation, or sometimes use the Halo model framework. It's even faster version of emulating what is captured in n-body simulations, but paste the baryons onto the n-body simulation and create the mock sky in much more computationally efficient way. So this is a method of choice if you're actually trying to do parameter estimation. Once you have a survey, you want to marginalize, you want to solve for cosmology if you're a cosmologist, or if you're an astrophysicist, you want to solve for the astrophysical parameter either by fixing cosmology or also by varying cosmology. And that is one of the analysis, the interpretation that we would have to do once we have this big data from cosmological survey. And really, this approach too is really the only practical method of choice for cosmological survey in the future. Okay, so those are the two approaches. Let's look at where we are in terms of our understanding of optical depth, and just zooming in on this particular quantity. So the hydro simulation seems to predict there are 3 simulations, non-radiative, no galaxy formation, with cooling and star formation, and then adding aging feedback on top of it. The optical depth is about, the range of optical depth is about the factor of 2, depending on simulations. Okay? So that's where we are in terms of hydro sim. Another approach is that you can actually take the simple analytical model, paste it onto n-body simulation, create the KSZ map. These authors have actually done this with feedback, without feedback. Without feedback, you actually see these are galaxy clusters that are moving toward us or that are moving away from us. And when you turn on the feedback, the sum of the peaks actually becomes more diffuse. What feedback does is that it puffs up the gas in the central regions and then pushing out the gas out the larger regions. So you see some of the well-defined peak in the central region is now puffed up. More specifically, this is the pairwise KSZ signal as a function of separation between the halo. And this is the prediction without feedback, with feedback. Here again, the two models, say that with and without feedback, makes a prediction. Predicts the KSZ pairwise velocity signal differ at the level of a factor of 2, not quite at the level of 20%. Okay, so that's where we are. Okay, so that doesn't seem, it seems difficult that we're going to get this 20% accuracy that we're actually looking for. So that gave us a pause. We thought a little bit about this, and we said, okay, well, the solution is probably there's some happy medium between those two methods. We want to use cosmological simulation for what it's good for. We can actually learn a great deal of the physical insights into cluster astrophysics, and we can learn a lot of information from the well-detailed zooming simulations. But then we need to find some ways of transferring that knowledge into the simplified model that are sufficiently fast so that we can actually apply it for the real cosmological analysis as well. So that's the strategy, is that we want to learn as much cluster astrophysics as possible from the current state-of-the-art cosmological hydro simulation, look for ways to extract the most important things that we have learned, identify them, put them into a simple analytical model, and then iterate a few times. Okay? So we've set out to actually do this by developing a zoom-in cosmological simulations of 500 megaparsec box called Omega 500 simulations, run with the 3 physics, simple non-radiative gas physics, just as a benchmark, adding cooling and star formation to form galaxies in these simulations, adding additional aging feedbacks to do additional feedback processes. So by using them, we're trying to characterize the importance of feedback physics as well as the cosmological accretion physics at the same time. Okay. The initial focus of our study was the outskirts of the galaxy clusters. At the time, this is one of the frontier. This is the image taken by Suzaku telescope and also Planck telescope, which mapped out the distribution of hot gas out to to several megaparsec. Okay. So now we actually, in galaxy cluster, we see those hot gas and baryons out to very large radii. Just to put this in a perspective, the R500, which is what's typically used for measuring cluster masses, is actually about this big, and this is the radius out to which the Chandra X-ray telescope can detect the photons out to, and also measure the temperature and so forth. Suzaku and also ultra-deep Chandra observation can extend this radii out to slightly larger radii, and that the SZ effect, which only depends linearly on density, can actually detect the gas out to even larger radii. And for the reference, there is a splashback radius that was discovered recently in simulation, which actually defines the physical outer boundary of the galaxy clusters. Okay. So what is the theoretical prediction before our work? So here's a comparison of the distribution of entropy profile, and there has been, over the last several decades, there has been a debate about whether or not that we can actually predict the entropy level in the central regions of the galaxy cluster, which has been, much of the work has been done, and the latest version of the SPH and mesh code seems to agree after correcting for some of the issues that were identified in SPH about the mixing of the gas. The hydrodynamic simulation can reliably predict at least in the adiabatic regime, the entropy level of the galaxy clusters. Throughout this time, when the cosmological comparison project was originally done in 1999, and then more recent version 2016, there's one thing that has been very robust throughout, which is the entropy level in the outskirts of the galaxy clusters. It just shows us that how robust those predictions has been. And what's remarkable is the observations are now reaching out to just only now starting to detect those baryons, where theoretical prediction could actually be reliable. Okay. So that was the good news. This is from the point of view of someone who's trying to use galaxy cluster. Still nonlinear, but the prediction seems to be robust. So this must be the region that we should be focusing on for the application of complex systems like galaxy clusters. Well, the initial results, however, was not as simple. So here's the results of the entropy profile measure using the Suzaku combined with Planck, and also the measurements of the gas fraction, the function of radius in Perseus cluster. And first thing that the observer actually found was that the entropy profile, instead of it monotonically increasing as predicted by simulations, you see flattening in the outskirts. The same goes for the gas fraction, that the gas fraction seems to exceed the cosmic baryon fraction, which was not at all expected for massive galaxy clusters. Okay, so the story doesn't quite hang together when you just with the first cut of the latest greatest simulations or the latest greatest observations. So that's around the early 2010-ish. And one of the resolution that we had proposed, a number of others have suggested, was that, well, this is probably because we're using X-ray, which depends on the density square quantity, that actually the gas clumping is one of the solutions. Here's one example. If the gas is clumped, then you're basically taking the average surface brightness profile, trying to convert the X-ray emission into the gas fraction, which has a 1 power of density. If the gas is clumped, then you tend to overestimate the gas mass, and that means that the entropy, which is defined as the temperature divided by density to the 2/3, you can actually explain this radially flattening entropy profile using clumping as an idea. This is an illustration from simulation, which seems to actually find more clumps as you go out into larger regions, and that makes sense, because these are the galaxies in clusters that has its own hot corona. When they enter into the high pressure region in galaxy clusters, these CGM or the group gas, they interact with the surrounding medium and they get stripped. So some of these, the X-ray emitting clump tend to disappear once you enter into the high pressure region like R500. In fact, the clumping is so small that has not been a problem inside of R500, but as you extend the measurement out to larger radii, the clumping is something that we need to take into account. This idea of clumping was born out by this, the Chandra, deep Chandra observations of April 133, and this is with the Chandra-like resolution, you can detect the AGN, you can subtract them, and with the careful analysis, you can detect something of order 70, 80 clumps in the outer regions. You can run the wavelet algorithm, you can remove them, and if you do, these Chandra observation, there is even some indication that there are some filamentary extended structure in the outskirts of the galaxy clusters, illustrating that these clumps are quite bright. Most of the X-ray emission around R200, 50% larger than R500. Most of the emission actually comes from these discrete sources, as opposed to the diffuse volume filling intracluster medium. So this is something that we need to keep in mind when we interpret X-ray observation. And at the same time, when you go deeper, you can also start to see some contribution from those filamentary-like structure, which also contribute beyond what you would naively get from the smoothly average, the X-ray surface brightness volume filling component of the clusters. So that's effect number one, the gas clumping, very important beyond R500. The second physics that is important is the turbulent motion, or the motions of gas in galaxy clusters. And this will be generated in the outer region. They are generated mostly by the cosmic accretion, how the galaxy cluster form and grow. And typically, the major merger generates significant motion in the interior of the galaxy clusters. But you always get this subsonic motions because galaxies are continue to fall. They move and perturbs the gas. So the velocity of order 300 kilometers per second is typical throughout the galaxy clusters. In fact, so this is a plot of the contribution of the gas motion, the pressure provided by the gas motion as a function of radius. And that the amount of gas motion is the contribution of gas motion relative is something of order 10 to 20% of the energetics of the galaxy clusters. But as you go out into the outskirts, where the accretion is actually happening, and where the dissipation time is getting longer, the non-thermal pressure fraction increases to a level of about 40–50%. So that's where actually real well measured in cosmological hydrodynamic simulation, and that actually depends on the rate of the mass accretion rate or dynamical state of the galaxy clusters. So depending on which cluster that you're looking at, the system that are actually accreting slowly would have something of order 10% of the energy in motions of gas compared to, in this case, 20%, depending on the dynamical state of the galaxy clusters. But more specifically, that this dependence actually is based on it comes from the diversity of the mass accretion history of the dark matter halos. So one can understand much of this plot by using a one-dimensional equation, which is basically consists of two parts. One is a injection of turbulence due to the mass accretion. So this is something that we know very well from simulations, the diversity of mass accretion history of the galaxy clusters, with some efficiency factor to convert the kinetic energy into driving of these motions. And this energy injection is then counteracted by the dissipation of the turbulence, which has some time scale. So at the end of the day, the time change in turbulent energy per unit mass depends on the competition of those two. And you can actually, this simple model can be actually used, and in fact, this is the analytical prediction, and this is the simulation results. And simulation results can be understood in this very simple term. So provided that if you can measure, or if you give the mass accretion history of the dark matter halo, we have a recipe, very simple model that predicts the level of motions as a function of radius for any given halo. Okay. And this motions of gas is important because if in one of the way that we weigh this massive galaxy cluster is to assume the hydrostatic equilibrium of the gas with the potential of the galaxy clusters, and that assumption is violated by the factor that we're talking about here, provided by if we neglect the motions of gas, the hydrostatic mass is expected to be biased, and at the level around R500, which is about 0.5 R200 me here, the bias is predicted to be of order 10 to 20%, depending on the galaxy cluster. The third effect that I'd like to talk about is the filamentary gas streams. The way the galaxy cluster grow is not through the simple spherical accretion, but much of the galaxy cluster growth happens through the streams of gas that are penetrating into the central region, feeding the galaxy clusters. So these filaments are actually a rather important mode of the growth of the galaxy clusters. So let's see, this is the density profile. There's a slight overdensity of filaments. And however, those crude filaments actually can penetrate sometimes all the way into about 10% of the virial radius, creating some very perturbed structure, and in some cases, it penetrates all the way into the core region. So you have this stream of gas that goes all the way in. So this is the results of hydrodynamical cosmological simulation. Of course, there's a question as to whether the all relevant hydrodynamic instabilities has been resolved. And no, in cosmological simulation, we don't quite have the resolution to resolve things like Kelvin-Helmholtz instability. The onset of the resolution is too low. So the prediction of this penetrating stream should be taken with some caution. And there's an ongoing detailed work on really understanding the stability of these cold streams. How far it can penetrate into is one of the active research area in this field. But taking this cold stream, it can actually comes all the way into the core regions of the galaxy cluster and create this thing like the cold front-like feature. This cold filament is actually interacting with the interior of the hot intracluster medium, and you can actually find sharp features. So this is a different way of forming cold front than having substructure falling in. Okay. So we can actually, these are kinds of information that we can learn about the interesting feature that can be generated in galaxy clusters. In the future, it would be interesting to actually, we're trying to actually do this Chandra Lynx mock analysis just to see whether we can detect these features with future survey. And this only with 10 kilosecond exposure compared to 1 megasecond. You can do a lot more with the future Lynx if we can actually get that up in space. And with deeper exposure, we can also start hope to actually detect some of the filaments in the outskirts of the clusters. Thank you. So I will like to summarize, actually say a couple, that this region in the outskirts of galaxy cluster, the physics of outskirts of galaxy cluster is quite different. Most of the physics is governed by the gas accretion and non-equilibrium phenomena in the outer region, and that's quite different from the central regions of the galaxy cluster, which has been the focus of much of the X-ray cluster studies, because that's where we get most of the signal, which has to do with heating, cooling of balance in the central system. So that's interesting. But some of the physics that we talked about is, but most of these gas accretion physics is something that we can actually capture with the existing cosmological simulation. We're not talking about the effect of feedback. In massive galaxy cluster, the feedback from the central AGN is not going to significantly perturb the energy in the outer regions of the galaxy clusters. Okay, so I think I have about 10 minutes. I will go through rather quickly. So that's why we think this is sort of a short list of what we think we've learned. And there are more story to the different types of physical processes that I did not have a chance to talk about, which I might talk at the ITC lunch tomorrow. So if you're interested in hearing about these other things, please come and join the ITC lunch. But based on this sort of the physical insights that we get about the cluster outskirts, we're now embarking on the new research program, trying to see if we can develop a simple analytical model for a purpose of cosmological surveys. The idea actually starts with a simple equation, assuming that the gas is in hydrostatic equilibrium with a gravitational potential. There is actually a way of injecting heat based from the feedback from stars in AGN, as well as taking into account the effect of the dynamical friction heating due to the orbiting galaxy. So these are some of the parameters, as well as the effect of stellar mass as a halo mass relation is parameterized in a rather simple way. And rather importantly, we are now putting in this model of the gas motions as a function of radius, which we have a simple 1D analytical model that depends on 3 numbers. And we can also have some simple ansatz and this is still work in development, of how the cooling heating balance in the central region might be modeled using the effective equation of state. Okay, so I'm going to fast forward a little bit. The main point of this, so we have this simple analytical model that capture much, and these are physically motivated model based on what we've learned from the hydro simulations. The nice thing about this model is that you can actually change the model parameter, which is difficult to do. Every time you change one of these parameters of dynamical friction heating or feedback heat feeding, we have to run the state-of-the-art cosmological simulation to even draw the line like this. Okay? Now we have a simple model. We can actually change the parameter fairly quickly. Each model takes about a few seconds, and then you can understand the impact of the dynamical friction heating, energy feedback, the effect of stellar mass, halo mass relation, and so forth, and how that impacts, for example, the optical depth of the galaxy cluster that I was talking about. You can do this also for the thermal Compton Y signal for thermal SZ effect and any other gaseous observable that we have in mind. The important aspect of this model is that when you tune these physically motivated parameters into the regime where the simulations are designed, for example, energy feedback is put in by hand in subgrid model, and so if you tune the feedback efficiency parameter and set that in an analytical simulation, that this model can reproduce in appropriate regime the predictions of the hydro simulation. Just illustrating that, because we built it that way, but we now have a way of getting the key observables. Instead of using millions of CPU times to run one model, it takes a few seconds to run one model. Okay? So once you have such a model, you can take that analytical model, paste it onto the large n-body simulation, and create things like the lensing map, Compton Y map, X-ray surface brightness map. Thank you. In rather significantly computationally cost-effective way. Another important thing about this analytical model is that we can actually calibrate that model, not to test it against simulation, but now we can take the existing Chandra data in the archive. So we have taken this, the density profile measurement and also the gas mass measurement as a function of mass from the literature, and you can constrain the model rather significantly well. What's remarkable about the Chandra measurement is the error bar is so tiny that we can constrain these parameters very strongly. This is just showing that the 8 parameters that we have in the model, how they're degenerate. And this is a constraint coming from the 2 set of observations. The density profile measurement as a function of redshift out to redshift of 1.3 for massive cluster from McDonough et al. 2013. And also the local measurements of gas mass, halo mass relation down to 10 to the 13 solar mass. Okay? So with that, here's my final word on one problem. The second problem I talked about. How well do we know the optical depth of the galaxy clusters? Now we have built a simple model, which we claim is physically motivated. We have taken the latest Chandra data to see if we can, how much knowledge we can extract from the existing data. The answer is that we can do better than 10% or 12%. Okay? On massive clusters, the optical depth is nailed down to at the level of about 4%. We know that very well. In low mass groups, it's good to about 12%. Our goal was to get to 20% or below, but with this sort of fast approach, we can actually get the optical depth calibration down to about 5 times 10 to the 13 solar masses. So problem solved, and we can go ahead and do cosmology for those particular halo masses. But there's a future direction. One is that we have mostly focused on massive galaxy cluster where we have a plethora of data out of the entire region of virialized region of galaxy clusters. But some of the KSZ, pairwise KSZ measurements are made all the way down to galactic scale. They're taking luminous red galaxies from galaxy survey and stacking the CMB signal at that locations, meaning that you're actually picking up the KSZ signal from 10 to the 12 Milky Way sized galaxies. So those are the circumgalactic medium, which we have much less understanding of. There's some scant understanding from the absorption studies on the density and temperature structure, but not as good, not well enough as in terms of constraining the density profile and temperature profile, especially density profile, which is all that matters for optical depth, at the level comparable to Chandra. So that's one of the future area. We need, this is also an area we really need simulations to understand the physical processes that are operating, affecting the CGM property, and extend the calibration, not just to observation because it doesn't exist, but we're trying to do this using simulations. Another frontier is to actually take these Z map and it's called a cross correlation. This is a way of detecting a small signal in massive complex data. By cross-correlating, picking the lensing peak, and then stacking studying the signal, the corresponding SZ signal, we can actually be studying the astrophysics in smaller objects, such as CGM. So this kind of study will give us more hints as to the physics of not on the massive cluster, not only on massive cluster, but also on galactic scales. frontier number 3, one of the important parameter for the X-ray survey is the amount of X-ray emission coming from the central region which emit most of the X-ray photons. So for that, we really need a better understanding of core region, which I haven't talked very much about. But there's a progress in this area from the latest simulations. For example, the Romula C simulation, where the Mila Chalina-Murray, who is here at SAO, is involved in. And with the latest simulation seems to indicate that the merger is important for the formation and disruption, in particular, of the core. This is an illustration that how entropy profile entropy has in the central regions of the galaxy cluster has increased precipitously when the galaxy cluster experienced head-on merger with low impact parameter. This is a 1-to-8 merger in this cosmological simulation of one of the highest resolution simulation with spatial resolution 250 parsec. So, and with that, you can actually see the disruption of core, which is telling us that perhaps the core formation, its evolution, the merger actually might be just as important as the AGN feedback. The insights that we get here is the AGN feedback is actually important for regulating the core, but it's really the major disruptions and head-on merger, low impact merger. And it doesn't have to be that like 1-to-1. It could be something like 1-to-10 is big enough to actually create to cause the core to be disrupted. And we've seen some example of that from the latest simulations. Okay. And then that the last, another frontier, number 4, is based on the work that's recently completed by Michelle here in the audience, and this is based on the idea that the simulations are becoming very realistic, and especially in the outer regions. We have some understanding of what the physical processes look like, and we can reproduce some of the latest observation in some exquisite way. So that opens up a possibility that perhaps you can use the AI technique, machine learning technique, to actually train this method, the data-driven method on the simulated cluster, in this case TNG simulations, and look for a way to actually reduce scatter in the cluster mass estimate. And indeed, the machine learning technique, in this case convolution neural network, seems to actually outperforms the traditional technique. So this is compared to core X size luminosity mass relation, which has typically the scatter of about 15 to 18%. If you actually use a machine learning technique, in some cases you can actually get the scatter of the cluster mass at the range of about 8 to 12%. So that seems very powerful. And Michelle has actually done this work trying to understand. But the question here is the machine learning technique, it looks like a black box. This reduction of high dimensional data into a single number seems to be like a black box to me. But by using this thing called Deep Dream, which is the sort of the image facial recognition technique, you can reverse engineer this to ask the following question. What changes in the inputs in the images, X-ray images of galaxy cluster, do you need to make in order to actually change the mass, increase the mass in this case? And what she has learned from this exercise is that, most of the pixels that are important for cluster mass estimations is in the outskirts of the galaxy cluster, but it tends to ignore the central region in about 20% of R500. Okay? Well, there's some exception where they're actually the equally bright core, and the machine learning even has a problem with defining which one is actually the central region. So in that case, there are some exceptional cases as well. So that's very encouraging. As I have been arguing, the central regions are difficult to model, so you would not want that machine learning to be learning too much on the central region. It's not. And however, this technique, of course, there's a philosophical questions that we could ask. We're still calibrating this technique on this simulated universe, and it's probably going to be only as good as the realism of the simulations. So more exhaustive studies of how realistic those outer regions of the X-ray emitting gas is modeled in current simulation is something that we need to continue to ask if we were to use this simulation-based machine learning approach. Okay? So I'll end here. The future of this cluster survey and cosmological survey more broadly, and cluster being one of the highest density peak that are just one of the brightest pixels in many of the images that we're going to be seeing, from optical to microwave to X-ray. Data is growing. It's going to be growing exponentially. The problem that we face in this field, and in particular, not only that the sensitivity is improving, but the angular resolution is improving, so we're going into the smaller nonlinear scales. and that's where we're going to be gaining a significant amount of information. The problem that we're facing is this multiscale, multiphysics, big data challenging problem. It has a lot of these big issues. And the solution that we're seeking, especially in this case of galaxy cluster, as just an example, is that I think we need some combination of technique, and we need to make effective use, creative use of each of these techniques, but use it in the right way. We need computer simulations to learn about the physics of the physical processes that are happening. And to learn more about the nonlinear physical process in the outskirts of the galaxy clusters, which I would argue that it's simple enough that the current cosmological simulation is doing a pretty good job, but we can do better. The analytical modeling is very important. We can actually, the simulation looks otherwise quite complex. We need analytical modeling to really dissect which physical processes are actually important and be able to learn from the simulation, put that into the simplified analytical model so that we can develop even the fast technique that are needed for interpreting big data. But then there's new technique, the data-driven technique based on machine learning, sometimes outperforms what we can do. And we've seen the example in the case of the calibrating the X-ray masses. The scatter is smaller. It's picking up on some features that we don't know, and we want to learn more about. But it's already outperforming what we have done so far. Okay. So there are a number of future directions. I started out with these discussions of galaxy clusters, but the future is to go down to smaller scale. As we improve the sensitivity and resolution, we're going to be seeing some of these signals in both CMB+LSS, as well as the future X-ray satellite like Lynx. We're going to be finding those gaseous systems in low mass, high redshift systems. We would want to be developing and better. So far, the analytical model I presented is focused solely on gas. There is just as much development on the analytical modeling or semi-analytic model of galaxy formation. Those two fields would have to come together so that we can start to model the gas and stellar component in a self-consistent way. And this is the field of baryon cycles. We would want to develop a unified model that allows us to model things like core evolution, or the relationship between the stellar properties and gas properties from the CGM to intracluster medium. But then at the same time, we would also want to exploit the sort of new technique, ways of actually detecting small signal from multi-waveband observation, and this technique is generally known as a cross-correlation. It's just a way of identifying the source and then asking the questions, what kind of signal can we extract from other surveys? This could be a powerful technique of extending the mass range and redshift range and just digging deeper into this otherwise fairly complex, rich data. We would also, I haven't talked about this too much, but the effect of baryons on dark matter is equally an important problem. And this is something that we can study more of with as we make increase the realism of the galaxy formation simulation. And the last but not least, the machine learning technique. It should be brought into the mix, but do this in a way that not just that you improve the performance, but you take this step to try to understand, not to use this as a black box, but to really understand what the machine learning is doing. And I think the future direction is there's some union of the physics-based approach and data-driven approach. They can go hand in hand. So this is something I think is something that the community as a whole has to think more about. There's some deep philosophical question as to whether we can do cosmology based on this AI-based technique. So I'll stop here and thank you for your attention.
Thank you. Other questions? Yes, Tony.
So, are these filaments that you're seeing in the X-rays or Merger-Induced, are they the same as the filaments from the dark matter models?
Dark matter models.
Yeah.
They are. Well, that's a very interesting question. It's something that ongoing we're actually trying to interpret whether they are same or not by trying to make mock images of what the filaments actually looks like. Jury's out. I don't know the answer to that question. But that's an interesting question. It's personally, the detected filament-like thing does look very bright. But the rigorous comparison has to be done to see if the lambda CDM simulation predicts the level of X-ray flux that are coming from the filaments. It's very much an ongoing process, yes. So I don't know the answer to the question, but maybe it's something that I can report to once we have completed the comparison and then see what the expected signal from the filaments from the simulations looks like and compare it to ABLE 133.
So in your analytical model, it seems to assume hydrostatic equilibrium, but we know now that for the observation there's also non-thermal pressure support. And that could be significant in cluster outskirts. Any plans for including that effect?
Right. So I should just, I went a little too quickly here, but I should just mention that this P here is actually a total pressure, which is a sum of the thermal and non-thermal pressure, and that the non-thermal pressure is modeled based on the analytical model that we talked about. So that has been put into this model. So this is how this is one of the important ingredients, which was actually missing from the original model. So you tend to overestimate the SZ flux by something of order 50%, if you or depending on where you're getting the signal. So that's a very important part. So if you put in a non-thermal pressure, you suppress the thermal SZ signal and also suppress the density, the optical depth as well. So, but that has been implemented now.
Which is on the order of 10%. So the question is, do you think you are missing some important ingredient in your simulation, or is more due to the different fraction of relaxed and disturbed systems so that you added the simulation with respect to the center?
Yes, that's an excellent question. So first thing I should point out that the amount of non-thermal pressure support ranges from something of order at the R500, the R200 mean is very large, but R500 is something of order 5 to 20% is the range. And that depends on the mass accretion history or dynamical state more broadly speaking. So, so the question here is, yes, we find the things that the bias of order 20%, that's true, but we also have systems that are 5%. That really depends on the mass accretion history in the simulations. So it is possible that with XCOP, typically the samples tends to be more round, more relaxed. So relaxed clusters tends to have the sort of the early mass accretion has not has much disturbances. So it's natural to expect that the non-thermal pressure is low compared to the average or median value. So for me, I don't think that's a surprising result. We should be asking about the selection function of the XCOP sample. And from the quick glance, the XCOP samples are mostly relaxed clusters. So that goes in a direct. So we should be once we pick the right simulated cluster that is representative of XCOP, I expect the number to be lower than just the simple median.
Any other question? If not, then let's thank Daisuke once again.
How you doing? Yes, very good.
Good to see you again.
Yes.
So I'll get to meet you on Friday.
Yes, yes,
Afternoon.
yes. So are you here in the building B or?
Yeah.
Okay.
Fifth floor, right next door.
Okay.
actually.
Okay, sounds
Not
good.
my neighbor.
All right, that sounds good. Yeah, look, how's everything?
Good, good. I'm back here now.
Yeah.
So, good. How about you?
I'm good. I mean, I'm actually in Germany right now, so I'm just flying back and I'm enjoying my sabbatical leave.
So is it a year or 6 months?
It's less than 6 months, 1 semester, so it's like 4 months.
Okay.
Yeah.
Okay. And you're at MP or MPA?
MPA.
MPA.
Yeah,
so
that's
it's
right.
Russia.
Right, right.
Oh, that's nice.
Yeah.
Perfect.
Yeah.
All right. I think the dinner is tonight.
Oh, that's right. Are you able to join us?
I will ask Akosh if he has a spot, but I would love to.
Okay, that would be great.
Hopefully, I'll see you today.
Okay, that would be great.
Well, hopefully, I'll see you tonight.
I'll see you tonight, yeah?
Friday.
Catch up, yes.
It was a great trip, by the way.
Oh, really? Okay, thank you. Yes.
But in one of those questions, that
Yep.
was actually a short speech.
Sure.